Hello. The name of our final project for deep learning is DeepCodi, and it's short for coronavirus diagnostic using deep neural networks. Our team consists of Adam Berkley, Chris Cataldo, Aaron Wang, and myself, Matthew Rodrigues. I'm going to be walking you through the project overview and then into data and pre-processing, and then I will hand over to my partner, Aaron Wang, who will continue with methodology and model architecture. So as we all know, the COVID-19 pandemic is severely impacting the health and well-being of countless people worldwide. COVID-19 causes chest abnormalities that are noticeable in chest x-rays. Our model attempts to learn these abnormalities, and based on the patient's chest x-ray, it predicts whether a patient is infected with coronavirus. We use a very recently available data set, and due to the general lack of availability of public COVID x-rays, the small size of the new data set, as well as the current relevance of COVID-19, we found this to be a new and novel challenge to tackle. We implemented 3 models based around the well-known VGG16 architecture, which is a deep convolutional neural network originally proposed in 2014. We found that pre-processing, data augmentation, and resampling to reduce class imbalance was crucial in the success of training the models. And due to this high class imbalance, we measure the performance of our model with a combination of metrics, including F-score, precision, specificity, and sensitivity, which is otherwise known as recall. We believe our results were really promising. Our best model, dubbed VGG RAND, was able to exceed our original evaluation metrics that we set out as a goal at the beginning of the project. And in addition, with a standard threshold of 0.5 for sensitivity and specificity, we were able to outperform the best model in the original paper that inspired this project and that released the data set we utilize. I'm going to walk through the pre-processing and the data. So we use the recently available COVID X-ray 5K dataset, which includes 184 COVID positive X-rays and 3,764 non-COVID X-rays. Classification models tend to perform optimally when the number of samples in each class are the same. Thus, a significant challenge we faced is the imbalance between positive and negative samples within the dataset. To overcome this, we use a combination of selective data augmentation and resampling. Data augmentation enlarges the size of a data set by applying a series of random transformations to each image in a batch during training. We used conservative amounts of horizontal and vertical shifting, shearing, and brightness shifting to selectively augment only the COVID-19 samples. Resampling is a technique used to adjust the class distribution of a data set by randomly resampling the training set, such that it reduces class imbalance. In general, there are 2 approaches. Whereas oversampling randomly duplicates images from the minority class, undersampling randomly removes examples from the majority class. Since we have only 184 COVID-19 samples, we opt to use oversampling. Together with selective augmentation, we found that this was really effective in reducing class imbalance and in fact improved the performance of our model significantly, down from a sensitivity rate of 77% and up to one of 91%. At this point, I'd like to hand over to Aaron, and he will cover methodology as well as model architecture.
Thanks, Matt. So as Matt said earlier, we evaluated the performance of 3 models. The first model is a baseline VGG16 model that is pre-trained on ImageNet. This transfer learning model is used as a feature extractor that is fed into a new classifier. And to do this, we freeze the pre-trained weights of VGG16 while training the extension layers of the classifier. The second model has the same architecture as VGG16, but is trained on our data set, that is the same as DeepCodi. The third model utilizes a novel CNN architecture similar to VGG16 that is also trained on our data set. In terms of parameters, we trained all three models for 10 epochs, as this was the number of epochs it took for the losses to converge. The models also utilized SGD and ATOM, minimizing the mean binary cross entropy loss. We found that the loss function was a crucial component in training the models successfully. Initially, we used some BCE loss, the intuition being that since the magnitude is typically large, the model might converge faster. However, we found our evaluation metrics to perform poorly when trained this way. Thus, we switched to mean binary cross entropy loss. The intuition being that since the mean binary cross entropy loss is more comparable in magnitude to sensitivity and specificity, we may be able to linearly combine them and train a model that is more sensitive to the metrics we care more about. However, we ultimately found that mean binary cross entropy loss alone performed the best. Next, we'll have Adam talk about our amazing results.
Thank you, Aaron. We focus on 4 different metrics for our results: dice coefficient, precision, sensitivity, and specificity. The Sorensen dice coefficient, which is equivalent to F1 score for binary classification, is used to measure the similarity between the predicted values and the ground truth, and it is more commonly used in image segmentation than classification. Precision gives a metric for how accurate the predicted COVID cases are. Sensitivity gives a metric for how well the model does at predicting COVID compared to the actual COVID numbers in the ground truth, whereas specificity gives a metric for how well the model predicts if a patient does not have COVID compared to the actual number of non-COVID images in the ground truth. A table with the exact formulas is included in the methodology section. Our results were very promising. You can see a full summary of the results in a table at the bottom of the page. We were able to exceed our original evaluation metrics that were set out as a goal at the beginning of the project, and with a standard threshold of 0.5 for sensitivity and specificity, we were able to outperform the best model in the paper that released our data set, which is displayed in the bar graph on the right. You can see that they were very similar for specificity at 0.99 and 0.98, which means that we both do well at identifying non-COVID patients. But our model shows an increased performance at predicting COVID, with ours getting a sensitivity of 0.94 to their 0.84. Now I'll hand this over to Chris, who will talk about the discussion and future work.
Thanks, Adam. So in conclusion, we wanted to highlight a few observations from our project. So first, just to cover the data set, as Matt mentioned when introducing our project, there isn't a substantially sized, clinically verified, and publicly available COVID-19 data set. The data set we used for this project only contained a small number of COVID-19 positive chest x-rays. So this was initially a significant problem as we needed to have enough data to be able to properly train our models. As a result, we heavily relied on our pre-processing and augmentation methods to achieve acceptable results. Ideally, it would have been better to approach this problem with a better data foundation, but given that this is a relatively new problem, we simply don't have a robust data set to work with. That said, this would be worth revisiting if a larger set of COVID chest x-rays ever becomes available. We also wanted to just touch on the model training. So our third model that Aaron had mentioned, the one that was inspired by the general VGG architecture, did not perform nearly as well as we had hoped. We just attribute that to the relative complexity of identifying minute differences between non-COVID and COVID positive x-rays, and just the lack of substantial training time to finally tune the model parameters. In addition, the modified VGG implementations that performed better also took a significant amount of time to train and required us to train the model overnight. So given the need to ensure that our metrics were accurate and for general debugging, we had to train these implementations multiple times which made our progress a bit slower and more difficult than we had originally anticipated. As for work in the future, we definitely would want to explore a cleaner and larger scale data set, and definitely data augmentation techniques that would remove prior markings made by radiologists, which again was one of the issues we encountered with some of our COVID positive data. In addition, we'd also want to look at and explore smaller and more compact model architectures that require less training time overall. That's it. So this was a very interesting project. We definitely learned a lot working with a sparse data set, and in the end, we found it incredibly worthwhile. So thanks for taking the time to listen. And if you have any questions, feel free to comment on DevPost.